second, we will study now the entropy production in the matter flow. Entropy production in the matter flow. Matter, in the matter flow, there is flow of matter. Matter always flows from high concentrated region to the low concentrated region. Okay, in towards the high concentration region, the number of moles of particular solute, they are high, but towards the low concentration region, the number of moles of the solute, they are low. That's why some particular system, it becomes highly concentrated while as compared to the other system. Okay, so there is basically the flow of matter from high concentrated region to the low concentrated region. Flow of matter means there is flow of some particular number of moles of the system. So for this type of flow, consider a system. Let us consider a system. This whole system is divided by some particular barrier, or at one side of the barrier there is different conditions, and on the other side the conditions are different. Let us suppose left side temperature of the system is T1 and chemical potential is mu1. On the right side temperature is T2 and chemical potential is mu2. Okay, so there this side basically is highly concentrated, this side is low concentrated region. Okay, also in this system we suppose that T1 system is lesser than T2. T1 is lesser than T2, means this is a cooler system and this is a hotter system. Okay, and we suppose that we transfer some particular curly n small number of moles from high concentrated region to the low concentrated region. Okay, now when some particular number of moles, they enters from first region to the second region, then there is then the heat content then the heat content, or you can say the heat of the solution, which is represented by dH. Okay, per mole increases. Heat per mole, this will becomes the partial molar enthalpy. This is the partial molar enthalpy. This also increases of the system. Since when we dissolve a particular solute into the solvent, the reaction is either endothermic or it is exothermic. Okay, endothermic or exothermic reaction, this is described by the heat content, or it is enthalpy. And when that enthalpy of the system, it changes with the addition of number of moles or removal of number of moles. So when the number of moles of one system changes and it is added to the other system, the heat content or partial molar enthalpy of the system, this increases. Okay, so during this transfer of the number of moles from one region to the second region, there are two types of heats which changes. Number one is there is increase in the partial molar enthalpy of the system. Secondly, due to this transfer, there is also heat of transfer. There is also additional heat of transfer, which is represented by Q star per mole. This is also added to the system. Now what is the heat of transfer? Some heat effects some heat effects are produced when a system from first region it changes to the second region at the surface of interface where some number of moles are changes, but other side number of moles are different. Left side are different, right side are different. So when the curly n number of moles crosses this barrier, then some heat effects are produced in the system. That heat effects, they are known as heat of transfer of some particular number of moles. So they are known as q star. Okay, so for the first region the total change in heat is hq plus q. Similarly, the same amount of heat it changes into h plus q star for the second side. Okay, so h plus q, this is the total change in heat of the system. Okay, so if this change in heat of the system, that always remains same for both regions, because if for the first region, let us suppose q1 is less and enthalpy is high, but for the second side system, q becomes high, h becomes low, to make this sum same as the region 1. So they will mutually adjust one another to keep themselves constant for the particular system. Okay, so now let's start their derivation. As we know, Gibbs free energy is given by G is equals to H minus Ts, and in terms of partial molar, apply bar here. From here, G bar is known as chemical potential. This is H minus Ts bar. Find out here Ts bar left side and mu is taken right side. Calculate entropy, partial molar entropy. This is equals to H minus mu divided by T. Okay, so they can be written as H divided by T minus mu divided by T. Okay, now H bar जो है, it should be replaced with H plus Q in studied system, in the present studied system. So after replacing, entropy becomes, only change this factor, H plus Q star divided by T minus mu divided by T. Okay, now partial molar entropy for the first region we will find for the first region and for the second region. For the first region and for the second region, enthalpy remains same. But for the first region the temperature is T1, for the second region temperature is T2. For the first region chemical potential is mu1, temperature is T1. For the second region chemical potential is T2, say temperature is T2. Okay, now overall the increase in entropy during the transfer of 1 mole of the matter from first region to the second region, only for 1 mole, the increase in entropy that is given by subtract the entropy of second system from entropy of first system from entropy of second system. So this minus this, so this is written as, you can see, ds bar s2, this is first term for s2 minus s1 माइनस माइनस प्लस हो गया. This is my this expression, and this is my this expression. Okay, so now simply rearrange this. First and third term, from first and third term, keep this as common. It will become 1 upon t2 minus 1 upon t1, plus from second and third term, combine second and fourth term, mu minus mu 2 divided by t2. Okay, so this is the increase in entropy. This is the increase in entropy per mole transfer of matter. But in the starting we studied that we transfer curly n number of moles, not one mole, some particular number of moles. So for the transfer of curly n number of moles and increase in the entropy of the system, this becomes, simply multiply this whole equation with curly n. Simply multiply this curly n. Everything remains same. Okay, and for small temperature differences, just like in the heat flow, for small temperature differences, we can say d, difference between mu by t, difference between the two regions. D represents here difference. This is written as second region, the same mu by t of second region minus mu by t of first region. So this expression from the above equation, the second term, it can be replaced with this one. Similarly, difference of 1 by t of both regions, it is 1 upon t2 minus 1 upon t1, second region minus first region. So this, in this expression, this is replaced with 1 by t. Okay, so ds bar, it can be written as curly n h bar plus q star into d of 1 by t plus d of mu divided by t, not mu divided by t, this will become minus, because this is t2 minus t1, this is t2 minus t1, here is t1 minus t2. Okay, so minus is taken as common. So this is the final expression for change in entropy of the system for the irreversible process when the matter flows from the system. Okay. So our first step completes. Now we now we will derive for the second step, which is the derivation for the entropy production. Okay, so let's start. Keep this as equation number 1. As we know, G is equals to T minus S, and in terms of per mole for open system, this will becomes G bar H bar minus T into S bar. G bar becomes chemical potential, H bar minus T into S bar. Divide this whole equation by temperature. So left side divide by temperature, right side divide by temperature. Okay, so we will get this expression. Now differentiate this equation. Differentiate this equation. Left side is differentiation of mu by t. Okay, so we have to find the expression for d mu by t and put this expression in this equation. Second term d by mu t. एक्सप्रेशन हम फाइंड करेंगे और फर्स्ट इक्वेशन में पुट करेंगे. ओके, so let's differentiate this is d h bar. I can write it as into product of 1 by t minus ds bar. Okay, so this is the first function, this is the second function. First function is taken as such, differentiation of second function plus second function differentiation of first function into minus ds. So apply here the rule of differentiation. First function differentiation of second function plus second function differentiation of first function. Okay, so this is equals to first term, it remains as such. Now we will do some changes in the second and third term. 1 by t is taken as common, this will become minus ts, t here multiply हो जाएगा. Okay, so this is equals to h bar d into 1 by t plus 1 by t. Enthalpy, as we know, enthalpy is equals to E plus PV. Okay, so when we apply partial molar enthalpy, partial molar internal energy, partial molar volume, so this is this expression is you studied in the closed thermodynamics in the graduation, that H is equals to E plus PV. So apply that expression here, D into E plus PV. Okay, minus second term is as such. Okay, this is equals to first term is as such plus 1 by T, open the bracket, dE bar plus d PB bar minus TDS bar, just open the bracket. In the next step, again apply the rule of differentiation. First function differentiation of second function plus second function differentiation of first function minus TDS. Okay, uh, again, as we know from the first law of thermodynamics, the expression for the first law of thermodynamics, first law states that change in internal energy, this is equals to change in heat minus PdV, work done in the system. This is the expression for the first law of thermodynamics. Put this value of dE in this expression. Okay, so we will get H into D into 1 by T plus 1 by T dq minus, sorry, here is curly q minus P V bar. Rest three terms, they are taken as such, there is no change. Okay, second and third term, it will cancel out, rest remains as such. As from the second law of thermodynamics, entropy, formula for entropy ds, this is given by change in heat with temperature. So curly q can be written as T into ds bar. Okay, so replace this curly q with TDS in this expression, so we will get D mu by T left side. See, on the right side first term is same plus 1 by T. First term is replaced with TDS bar. Second and third term, they kept as such. Okay, so you can see first and third term, it will cancel out. We are left only with the two terms. First term plus second term, V divided by T into differentiation of mu by T. Now put this expression in equation number 1. In this expression, In the second term, put this value, we will get d as irreversible. This is equals to first term minus ये second term जो थी this one, this is replaced with this one. Okay, in the next step, open this bracket, multiply h with d 1 by t and then q with d 1 by t. Next two terms, they are taken as such. First and third term cancel out, we are left only with second and fourth term. So this is the final expression for irreversible entropy of the matter flow system. Entropy production is given by 1 upon A into dx, change in this entropy with dt. So in the next step, simply put this d as irreversible from this expression into this. This will become curly n with dt into bracket starts q star d1 by t minus v dash dp divided by t. Okay. Now simply rearrange these terms, negative, negative, positive, 1 by a, curly n with dt. This is taken in a bracket with a. Okay, this is one bracket. Dx is taken outside and then bracket starts. This is just the rearrangement of the various terms. Okay, this is equals to entropy production minus this first bracket. Here there is change in the number of moles, so this will becomes matter flux divided by next 1 by dx into bracket starts. This is what? This is the matter flux of the system, and this is known as entropy production in matter flow. Okay, so we are left with the third flow, which is in the entropy production in a particular chemical process.